continue with our discussion on logic design. This is the second part of the lecture, logic design part 2. Now, you recall in our earlier lecture we talked about multiplexers. So, continuing with this discussion, we talk about another kind of a basic building block which is similar to a multiplexer, but it can be considered as its inverse or reverse. This is called a demultiplexer. Let us start with that, a demultiplexer. So, why we say this is an inverse? This works in a reverse manner as compared to a multiplexer. You see, for a multiplexer there are many inputs and one output, okay? Many inputs and one output. Depending on the select line, one of the inputs is selected. But in a demultiplexer there will be one input, but many outputs. Depending on the select line, the input will be connected to one of the outputs. This is why we call it the reverse or inverse. So, a demultiplexer will be having n number of output lines, let us call it d0 to dn minus 1. So, just like a multiplexer, there will be m number of input lines where n equal to 2 to the power m, and there will be one data input line here, let us say in. So, the way the demultiplexer will function is very similar to multiplexer, just the reverse of it. When S is 0, that means it is all 0, in will be connected to D0. If S is 1, in will be connected to D1. If S is 2, in will be connected to D2 and so on, right. This is called a 1 to 2 to the power m, because there are 2 to the power m outputs, n is 2 to the power m demultiplexer. Okay. So, as I said, a demultiplexer looks like this. There is one input, n number of outputs, and select lines which will be selecting one of the outputs, the input will be connected to that. Now, you may think where we can apply or what are the applications of this demultiplexers and so on. There are many applications in fact, but one application I would like to just highlight, their use in data communication. Let us consider a scenario. Suppose I have a multiplexer here. Let us consider 4 input multiplexer, and on the other side let us say I have a demultiplexer. Let us say here also there are 4 outputs. So, multiplexer is having one output, demux is having one input, and suppose they are connected, let us say over a long distance connection line they are connected. So, mux will have 2 select lines, demux will also have 2 select lines. Let us say these inputs are connected to A, B, C, D, some input sources, and these outputs of the demuxes are connected to, let us say W, X, Y, Z. Now, you imagine that this is something like a telephone exchange. You think of the older telephone exchanges which we had many years back, where you used to dial the numbers and using some switches in the exchanges the connection used to get established. So, conceptually this is something like that. Suppose A, B, C, D are subscribers, W, X, Y, Z are also subscribers. Let us say B is trying to make a call to Y. So, what the telephone exchange will do, the telephone exchange will be applying 0 1 to the select line of here, so that B gets selected, and it will apply 1 0 to the select line here, so that this output gets selected. So, ultimately this B will be available on this line and this will get connected to Y. So, for multi-party communication, this kind of multiplexer demultiplexer pair can be very useful, as this simple example shows you. right. Okay. Let us move on. Let us see how we can implement a small demultiplexer. There is one input and there are two outputs. First, again let us consider a truth table approach. This is a very simple case, there are only two inputs, there is in, there is S0 and there are two outputs D1, D0. So, inputs can be 0, 0, 0, 1, 1, 0 and 1, 1. Now, if the input is 0, 0, select line is 0. So, this 0 will go to D0. If select line is 1, input will go to D1. Select line is 0, this input 1 will go to D0 and if it is 1, it will go to D1. Now, I am assuming the output which are not selected, they will remain at 0. So, this is my function. So, if you construct the truth table, you can even see that this cannot be minimized any further. So, what did D0 indicate? D0 has a single 1 here. This is S0 bar into in. You see D0 is S0 bar in and D1 is S0 in. So, if you want to implement it, you just need two AND gates. They will be generating D0 and D1 and this input in will be connected to both and S0 will be connected directly to here and via a NOT gate to here. This will be the simple implementation for one-to-one mux using gates, right. Just implement these two functions, just 3 gates you require. Okay. Fine. Now, think of a larger demux. It is a 1 to 4. Because there are 4 outputs, there will be 2 select lines. Now, again instead of going through the truth table, let us try to find out how we can directly write down the expressions. You see D0 will be what? I am saying in will go to D0 if both S0, 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 S1 are 0 and 0. So, we write it like this: S1 bar, S0 bar in. AND of these 3. D1 will be S1 is 0, S0 is 1, S1 bar is 0 in. D2 is similarly S1 S0 bar 1 0 and D3 is 1 1. So, how we can implement this? Very easily, we would be requiring 4 AND gates to generate the 4 outputs D0, D1, D2 and D3. Let us say one of the inputs is common to all. This is connected, common to all of them, that is your in. And this S0 and S1 which are there, let us say that we have also have some NOT gates connected. So, we have S0 bar and S1 bar available with us. This is S0 bar, this is S1 bar. So, in the first gate for D0 I need to connect S1 bar and S0 bar. So, I connect S0 bar, I connect S1 bar. For D1 I need S1 bar and S0. So, I need S1 bar and S0 like this. For D2 I need S1 and S0 bar. So, I need S1 and S0 bar, S0 bar is this, S0 bar this, and D3 I need S1 S0. I connect S1, I connect S0, just like this. You look at this expression, just connect either S0 and S0 bar, S1 and S1 bar accordingly. So, you get a demultiplexer circuit, right, quite simple, fine. Now, let us come to a special kind of a demultiplexer. It has a different name, it is called a decoder. Decoder you can say is a special type of a demultiplexer, but it has very specific and different kinds of applications. So, what is a decoder? As I said, this is a special case of a demultiplexer. What kind of a special case? You can say that I have a demultiplexer where there was one input and there are several outputs and select lines. So, I am assuming that the input line is always equal to 1. So, under that special case I shall be calling this a decoder, and because I am assuming this to be always 1. So, this input need not be connected explicitly. So, I will say that only my inputs are the select lines and my only output are the just the output lines. So, a decoder essentially will be having n number of inputs and 2 to the power n number of outputs, let us say, right, depending on the applied input. So, whatever you are applying, exactly one of the output will be set to 1 while the others are set to 0. Like, let us take an example. Suppose I have a decoder with 2 inputs and 4 outputs. Let us say I have applied 0 1, 0 1 means 1. So, 0 1, let us say this line will be set to 1, all others line will be set to 0. If I apply everything 1 1, then the last line will be 1, others will be 0. Now, the point to notice that which we have mentioned here is that some decoders are available where the reverse convention is followed. So, what is the reverse convention? It says that the line which is selected, that will be set to 0 and all others are set to 1. So, you see design is the same, just on the output as if you are connecting a NOT gate, right. So, either you follow this convention or you follow this convention. There are many applications of a decoder, like when you have many functional block, for example, memory in a computer system, there can be many memory modules. Depending on the address, you have to select one of the modules, you can use a decoder to select that. So, there are many applications, we are not talking about them right now. Some of the applications we shall be seeing later possibly, but not right now. There are other applications like code conversions, data distribution and many others. Okay. Let us take a specific case, a 2 to 4 decoder. So, you have a 2 to 4 decoder where there are 2 inputs, 4 outputs. Look at the truth table. Depending on the data input, let us say if it is 0 0, then F0 is set to 1 for, let us say I am following this convention, the others are 0, the line selected is 1. If it is 0 1, F1 is selected, 1 0, F2 is selected and 1 1, F3 is selected. Now, here also you can straight away write down the expressions for the 4 outputs. You see F0 will be 1 only when D1 D0 are 0 0. So, you can straight away write F0 equal to D1 bar D0 bar. Similarly, F1 will be 1 when it is 0 1, D1 bar D0, F2 1 0, D1 D0 bar, and finally F3 1 1, D1 D0. So, again just to implement decoder you need 4 AND gates, okay. All of them will be 2 inputs. This will be generating the 4 outputs F0, F1, F2, F3, and the inputs you apply accordingly. D0, D1 are there, you will be requiring 2 NOT gates, you can apply the inputs accordingly, right. Okay. Now, the point to note is that the decoders that are available that we use, they typically has another input called enable. Like normally a decoder has 2 inputs and 4 outputs, like here 2 to the 4 decoder. There will be another input called enable, using which I can disable the decoder if I want. The idea is that if a decoder is disabled, then irrespective of what you apply in the input, none of the outputs will get selected. Only when a decoder is enabled, then only depending on the input, the respective output will get selected. Now, this feature you require when you have many decoders. I will take an example later, and you need to select one of the decoders. So, you enable one of them, you disable all others. The concept is like this. Okay. Now, in this case the truth table will be very similar. The only thing is that I have an extra input called G, where the normal operation of the decoder, which is shown in the first 4 columns, the G is 0, but when G is 1, G 0 means I am assuming that this is active low, that means G equal to 0 means the decoder is active, and G equal to 1 means the decoder is disabled. So, when the decoder G is 1, irrespective of what you applied in the input, the outputs will all be 0, none of them will be selected, right. So, in the expressions for the outputs, they will be similar, only you add a literal G bar to all of them, because they will be 1 if G is also 0. So, G bar will get added. So, you will be needing the AND gates here, which will be 3 inputs each. In the same way you can implement, right. Okay. Let us take some examples. Suppose I have a smaller decoder, 2 to 4 decoders, these are available to me. So, I have this kind of decoder available to me, 2 inputs, 4 outputs and an enable, but I want to design a larger decoder, 4 inputs and 16 outputs. So, how do you do it? Now, here we shall be showing you the design. The basic idea is like this: we will be requiring 5 such smaller decoders. In what way? The decoders will be connected somehow like this, in somewhat in this fashion. Well, I shall be showing you the detailed diagram. There are 4 2 to 4 decoders, there will be 2 inputs, 4 output each. So, this will make 16 outputs, and there will be another decoder which will also be a 2 to 4 decoder. This decoder actually will be selecting one of these 4 decoders. So, depending on what you apply here, one of these 4 decoders will get selected, and depending on what you apply in the input of that decoder, the corresponding output will get selected. This is the basic concept regarding the construction of the 4 to 16 decoder here. Let us see. So, here I have the schematic. Let me complete the connections. So, what do we want here? Okay, just a second. Let me just make this. There is a formatting issue. Let me correct this. This is 15, this is 10 and this is 11. Okay. Fine. So, let us have this. So, now we have a 4 to 16 decoder. Let us consider how our 4 to 16 decoder will look like. Our 4 to 16 decoder, let us say there will be 4 inputs. Let us call them A, B, C, D, where A is the most significant bit, D is the least significant bit. So, let us see how we connect the inputs to the decoder. What we say is that we will be connecting A and B here, the most significant 2 bits of the decoder, and C D we connect to the inputs of the other 4 decoders. Now, you see, as I said in the previous diagram, that the 16 outputs are generated by these 4 decoders, F 0 to F 3 here, F 4 to F 7 here, F 8 to F 11 here, and F 12 to F 15 here. And this decoder, what it does, this will be selecting one of the 4 decoders. This is the first decoder, this is the second decoder, this is the third decoder, and this is the fourth decoder. And this will be the enable of the whole decoder. This is the G of this 4 to 16 decoder. Let us see how this works. So, as it said, this A, B, C, D are the 4 select lines. Let us take some examples. Suppose I have applied 0, 0, 0 and 0. So, under this condition F 0 is supposed to get selected, that means F 0 should be 1, all others should be 0. Let us see how it works. Since A B is 0, 0, for the first decoder this one only will be 1, all others will be zeros, or the reverse. So, let us consider, if we consider the convention that we have followed, then we will be connecting a NOT gate here. Let us assume there is also a NOT gate in between here, they are connected via NOT gates. So, if this is 1, so this decoder will be selected, but these are all 0, 0, 0. So, these enables will be 1, 1, 1, these are not selected, not selected, not selected. And C D is also 0, 0. So, C D is 0, 0 means this F 0 will get selected. Now, let us say I apply 0, 0, 1, 0. Because A B is 0, 0, again this one will be selected, this line. C D is 1, 0 means this is the decoder which is selected, C D 1, 0 means the third line, this F 2 will be selected, that is correct. Let us take another example. Suppose I apply 1, 0, 1, 1. 1, 0, 1, 1 which is supposed to be selected is 10 and 1 11, this F 11 is supposed to be selected. Let us see how. In A B I have applied 1, 0, in A B I have applied 1, 0. So, in the output this is not the case, because it is 1, 0, this line will be selected, the third line, the others will not be selected. Because the third line is selected, this will be 0, and now this decoder will be selected. Now, C D I have applied 1, 1, 1, 1, it will select the last one F 11. So, you see this works. So, in this way we can very systematically design an arbitrary 4 by 16 decoder using 2 to 4 decoder. Now, as I said, there are many applications where you need to design very large decoders. So, it is important to know how such smaller decoders can be connected, we say cascaded together to form larger decoders. So, using this very small example, I think I am able to show you how smaller decoders can be used to construct larger decoders. In this example, we had used 2 to 4 decoders to construct a 4 to 16 decoder. Okay. So, the last thing we consider here is that how we can implement logic functions. Can we implement logic functions using decoder also? We say that, well, yes, it may not be very natural, people may not be doing it because multiplexers are much more convenient, but decoders can also be used to implement some logic function, implement some truth table. Let us see how. So, the idea is that you use an n by 2 to the power n decoder and an OR gate to implement a function of n variables. So, how do we do it? Let us take an example. Let us consider an example. Let us say that I have a truth table. Consider a truth table. Say this is a 3 variable function a, b, c and f. These are the inputs. Let us say the output column looks like this. There are 5 ones in the truth table. So, in terms of the function representation, you can also write it like this. This represents the function sigma notation. It is 0, 3, 4, 6, 7, 0, 3, 4, 6 and 7. Now, how we can implement using decoder? What we say is that we take a 3 to 8 decoder. So, we connect the 3 inputs here A, B, C. There will be 8 outputs. This 8 outputs will be corresponding to the different combinations of A, B, C to get selected. I am just writing down the numbers 0, 1, 2, 3, 4, 5, 6 and 7. Now, you look at this, what are the minterms that are true minterms 0, 3, 4, 6, 7, you connect an OR gate here. 0 connect one input 0, 3 connect 3, 4 connect 4, 6 connect 6, connect 7. This will be your output. So, it is easy to see how it works. Depending on the ABC value, if one of the true minterms is applied, so the corresponding output will be 1. Let us say you applied 0, 1, 1. So, this one will be 1. This is an OR gate. If any one of the input is 1, the output will be 1. So, in this way you can implement the function, right, very simply. But you may need a larger OR gate with large number of inputs depending on how many ones are there in your function, right. Okay. So, this is another example. So, you can similarly work out here. If we apply A, B, C, again you have the 8 outputs. Here the true minterms are this 0, 0, 1, which is this 1, 0, 0, 4, 1, 2, 3, 4, this one 5 and 6, 5 and 6. Connect them to the OR gate. This will be a function. Okay. So, these are also very programmable kind of a thing. The decoder remains the same, only the OR gate and how you connect them, that will vary. You can implement any arbitrary function. Okay. All right. So, with this we come to the end of this lecture. Now, we shall be continuing with our discussion in the next lecture, where we shall be talking about some other kind of building blocks, some special kind of decoders and other building blocks that are also very useful in logic design. Thank you.